Thank you for organizing that, Magdi as well. So today I'm going to talk about risk and robustness, but I'll start with sharing some of my experience being this workshop that is forward-looking. So we know that RL is really about sequential decision-making, and this is the kind of problem that we've been working on. So this is Tetris. This is a sort of a game. We've worked a lot on games. This is the real success of RL. So for those of you who don't know, RL has been most successful in finance. The reason that you don't hear about it is because it is successful. So this is just an American put option. It's a contract that gives the owner the right to sell stock at a strike price K at a maturity time T. So if you're above the strike price and you sell it, you make money. If you're below the strike price, you don't want to sell it. So this is probably the field where RL has currently most real-world applications. This is a maze-type domain, the pinball domain, which I think most of you know. It's a stochastic shortest path problem. So this is a problem that we know more or less how to solve. And I'll talk about those problems in the context of risk and robustness. But before that, let me sort of show this once again, this graph that you've seen about 1 million times today. So this is a classical view of RL. There is an agent here, and there is a control entity. The agent has actions. It observes something. It gets something, and this is really how we teach our students. What I'm going to argue, this view is wrong, and this view is nice to tell ourselves, but it's something that you don't really see in real-world applications. So in the classical models, we know the states, we know the actions, we don't know the transition or the reward. We need to learn them, whether we do it in a model-based, model-free. Somehow we try to learn them, and this is usually our objective. This is a really mathematically appeasing setup, but it's not something that is really useful because it's a bit too far from reality. So this is a paraphrase on Box's famous saying. So in the last few years, we have lots of algorithms, and those in the crowd who are co-authors of other algorithms, please excuse me. We have many algorithms, but I think we have very few real-world successes. As I said, the only real-world success I'm aware of is in finance. But other than that, I'm not aware of many other real-world successes. I know that Chaba here is organizing a journal that is a special issue about real-world successes. I look forward to that. Yeah.
I would say that personalization, like contextual data style, is a real-world success.
Well, I mean, it's contextual bandit, so there is no notion of state, but yeah.
There is a reward.
There is a reward.
It is reinforcement learning.
Sort of. So here is one reason why we think we're that good. So this is one thing that we're doing at reductionist fallacies. So this is a mental fallacy that is written here. So you would agree that only smart people can play Go or chess or shogi very well. Surely you agree with that. You agree that everybody can tell a joke, or almost everybody. So the logical conclusion is, and we know that computers are really good at Go, chess, or shogi. Hence, computers can easily tell a joke. That's not quite the case. So we make, because some isolated tasks are very difficult for us, like playing Go, and because computers are very good at Go, we think we're almost there. But if there is one book that I would recommend that you guys read, it's the book from the former MIT Media Lab director, Resisting Reduction. So when we think about our field, we also do a reduction, and we're trying to make it look like we're almost there, but we're not there. So people talk about AGI and even AI. So when I started in the field, as Elad said a long time ago, I wanted to build whether Terminator or Commander Data was depending on the mood, or maybe even Smith. But this is the level of robots that we have now. So this is the truth. Okay, this is what we know how to do. This is from a few years ago. We're not much better. Okay, this is where we are. So we're really not that good. And before I tell you why we're not that good, so I want to emphasize that there are really three types of RL problems. There is what's known as a static RL problem. In the case here of Pac-Man, imagine that you just have Pac-Man and you need to eat all the fruits. So basically there are no ghosts, there are no other agents. There are dynamic problems where there are other agents, but they don't care about you, so the ghosts do not react to Pac-Man. Those are two very easy problems. And then there is the counterfactual type of RL, where the other agents respond to you, and you need to expect or to predict what they will do. So really, we were pretty good at static RL. We're not bad at dynamic RL. And I would argue that we're just not very good at counterfactual RL. Like, we don't have good ways to predict other agents. And in the last year and a half, my company was acquired by Ford a year and a half ago, and I've been working on autonomous driving. That's, you would say, a classical RL problem. And what you get from talking to the product managers is what they really care about. And that's what I want to convey in the next few minutes. So calling it an RL problem is a gross oversimplification. Understanding the reward is very difficult. Killing someone is bad. Not killing someone is good. We got that. But getting a reward function in the classical way of RL is incredibly difficult. Some would say impossible. The state is humongous. What I know and what I observe is very difficult. And also understanding the action is something that is very, very complicated. So we have, eventually the actions are gas, brake, steering. There are no other actions. But understanding the right level of abstraction is a real challenge for those systems. So even though it appears to be an RL problem, there are many other problems that need to be solved. And the right, or I think a less wrong approach is what is known as extended intelligence. So you do have the agent here, the same way we had before, but there are other agents you need to communicate with. So in a self-driving car example, the non-level 5, the level 4, level 3, there is a driver. You need to, in the driver's seat, or maybe there is a passenger not in the driver's seat. You need to communicate with this agent. You need to be able to explain what you do. And there are other agents that are abound that also affect what you do, whether it's other drivers, pedestrians, and so forth. So basically, the right way to think about the system is that your agent is going to be situated in a much more complex environment where it has to connect, to talk, to communicate, and to reason with other agents. So it's not just a multi-agency issue, it's just an issue of understanding your place. So this leads to 5 principles. Maybe there are more. Those are the 5 principles that were discussed between product managers and myself, and those are how you should build an AI system. At least you need to be cognizant of what's going on. So the first one is awareness. The system has to know how well it performs and be able to communicate its performance. The second one is accountability. You need to explain what you do, either in words, by computation, and either in some interpretable mean. The third is adaptivity. So you need to be able to adapt to conditions that you've never seen before, or to conditions that you have seen before, but you're not sure exactly what they are. The fourth, and perhaps the most important one, and the one most neglected by our community, is that of lifecycle consciousness. So we need to build systems that can be debugged, whether they can be debugged as unit testing, whether they have some sort of decomposability. We need to build systems that you know that are going to put into production and eventually deprecate all the way. So being able to build a system that is lifecycle conscious, not just by its performance, that's a real challenge. And last but not least, scalability with resources. The more data you have in terms of data and compute, the better your policy should be. So what I'm arguing that every type of research that I will do in the future, I have to view it through the lens of those principles. And you should notice those are design principles, so they're not coming from the side of the RL researcher. They're coming from the other side, of somebody who's going to use RL. They want to make sure the system is aware. They want to make sure the system is accountable, that it's adaptive, that you can actually work with it in the real world in terms of debugging, testing, and so forth. And scalability, that's more of our thing. We want to build things that actually work in the real world and can take a lot of data in. So this is more of a manifesto. Now I'm going to go to more mundane part of the talk. So are there any questions now? Philosophical or political?
Question.
Yeah.
So does formal verification also fit into this framework somehow?
So verification goes into the life cycle consciousness. It's a crucial aspect. I mean, you will not drive a self-driving car outside of California or the US will have to be verified. I mean, the laws are just very, very clear about that in Europe, at least. So you need to be much more clear about how you verify your system and how you get some sort of confidence that it's actually going to work. Okay. So this is my agenda. So I want you to develop. That's something that I've done for many years. And the way I view the problems now is that whenever I have a research topic, I look at this spider graph between scalability, awareness, adaptivity, accountability, and life cycle. And today I'm going to talk about risk sensitivity and robustness. And that's really about scalability, adaptivity, and accountability. And to a lesser extent, awareness and life cycle consciousness. And I think that's a useful way to think about research problems in our field. And I would urge you to think about whether you're contributing to awareness, scalability, adaptivity, accountability, or life cycle, or whether you're just writing algorithms that, there are already so many algorithms, not clear why we need that many more. So let's start with some motivation for the risk-sensitive part. So why should I be risk-sensitive? So this is a pinball domain. I have a blue ball that I want to get to the red dot, but it's a pinball, so everything shakes. And there are really two choices. I can take the upper route, which is longer but safer. So the distance between the two walls is large. Or I can take the lower route, which is the distance where the distance is smaller. So it's a little bit less safe. And you see here that there are two distributions of time. So the question is, which one do I prefer? Well, it really depends, right? If you think about it like getting to the airport, so if I need to get to the airport around here, then probably I don't really care if I'm going to get a lot earlier to the airport. I don't enjoy being there very much anyway, so I might as well take the safer route and make sure that I'm going to get there on time, though later on expectation. So what we see here is the risk awareness, so being aware of the risk, or the tail risk in that case, gets me something which is intuitively more robust. So if I take the upper route, it looks like intuitively my policy is going to be more robust. Okay, so let me just tell you about three types of uncertainties. And we'll explain what robustness is meant and what risk is, how risk is measured. So there is a parameter uncertainty. Basically, I don't know the MDP parameters, so I'm solving a max-min problem, and I'm looking at a maximum over policy, minimum over all parameters. So that's a classical problem in a robust control. There is an inherent uncertainty. Basically, I look at a single trajectory. I have a cumulative reward, but expectation does not quite catch the variability. For example, here the expectation is the same, but I'm sure most of you will not mind playing on $1, but on $1,000 or $10,000, maybe you'll be more hesitant. So inherent uncertainty is measured by variability, and you can look, for example, at functions like maximum over the policy, and this is some risk measure. For example, this is variance adjusted risk. For those of you who like finance, this is known as the Markowitz risk measure. So this gives you some explicit safety measure against unluckiness, and there are tons of studies that show that humans tend to be risk aware. Whether they're risk seeking or risk averse, that's a different story. And last but not least, there is the issue of model uncertainty, often neglected. So model uncertainty means that I just actually don't know the model. So there are several models here. My policy is defined in a space which does not depend on the model. And there is a model mismatch here. So for example, my policy looks at the input and the model itself. Some of them are Markov, some are not Markov. So the family here of models can be quite complicated. So those are the three types of uncertainty. And we look at risk often when the cost of failure is high, but also when the model is not known and when we get it from a few samples. So getting a model from a few samples is an interesting problem. Sometimes we just have a lot of uncertainty. For example, if you're trying to fit a model for a single user, that can lead to a lot of uncertainty. And the main three properties the main three design principles that we're trying to follow here are scalability. That's going to mean that we'll have to use approximation architecture or deep learning. Adaptivity, that's the robustness aspect or the risk sensitivity aspect. And accountability, which means that we'll have to be able to explain ourselves to someone else. So what about complexity? So everything that I'm going to talk about today is very hard. Some of it is not known how hard it is, but most risk problems are really hard. So let's not talk about exact solutions. That's not going to happen. And there are quite a few other papers on that. So we have three parts for this talk. In the first one, I'm going to tell you about robust MDPs with function approximation. And then I'm going to tell you about CVaR, conditional value at risk, which Emma mentioned yesterday. And last but not least, I'm going to point to the two main problems that remain for both approaches and how they can, what are the remedies that we have for them. So let's talk about robust MDPs. So this is just explaining the model. This is a planning problem, so everything is known. We're looking for a policy, but this is a classical MDP, so we know the transition probability from S0 to S1 is 2 and S3. But in a robust problem, we're not sure exactly what is this distribution. It can be in some range. In this case, it can be based on confidence intervals or any other form. And we know that those are potentially very harmful. Okay, so the definition of a robust MDP, the state action rewards are the same as the standard model. The transitions belong to a set, so the conditional transition between state S given action A to S prime is not precisely known, and we're looking still for policy pi, and our objective is the worst case objective, so it's a sup-inf of expected return, and here the infimum over the model. So the way you should think about it is that you choose a policy, and then the adversary is going to choose a model that is worst for your policy. What can we do? We can define the value function. This is going to be for a fixed policy for now, as the infimum over all models of the expected return. So this is the worst case model for my chosen policy. So in this case, when I want to think about it, then there is a very clever adversary that knows my policy, and then this adversary computes the worst possible model. So this may be this point here, and maybe somewhere in the middle here. And as I'm going to move around, this adversary is going to keep the worst possible model against me. So this vicious adversary is really going to hurt me continuously. And you can write a robust Bellman equation for a fixed policy, which looks like that. So it's not a linear equation anymore. So it's V pi equals R plus the discount factors time, in this case, there is an infimum over all possible models. So for small problems, you can show that this is a contraction. You can, even if you look at the Bellman equation, you can show that everything works. But for large problems, this is not going to end up well. Okay, so you can do dynamic programming for small problems. And then what do we do when you want to solve large problems? So approximate value function. The classical approach is that I'm inventing some features. And those features are approximated in a linear fashion. So phi is known and fixed. W is some vector, and I want to select it somehow. So the standard non-robust approach will be I'm going to sample many samples from using pi, and then I'm just going to regress W. So I'm just going to regress this function using my favorite regression algorithm, and voila, I have an approximation. I can do value iteration or a policy iteration, whatever I want at this point. So what's the problem? Why can't I do it for a robust optimization situation? I know I'm after lunch, but come on, what's the problem? Why can't I sample? because I need to sample it from the worst case model, right? So I do not know how to sample it from a bad model. I don't know this model. This adversary is supposed to bring this adversary to me. So I cannot regress W because I don't know how to sample trajectories from the worst case model, right? For a robust problem, the value function is equal to the infimum over all models. And this infimum is something I don't know how to sample from. Okay, so that's a bummer. So what is our approach? So the idea is to use the age-old concept of bootstrapping. So basically, we have the Bellman equation for a fixed policy. And then the algorithm is really going to be very simple. I'm going to, at any iteration, I'm going to sample our regression targets. And those, I'm going to use these regression targets. So this is going to be, I have my x's. I'm going to treat them as if they're the correct ones. So I'm going to generate yi's by solving this equation. Remember, this is a planning problem, so p is known. And then I'm going to iterate and solve for the next wk plus 1, the next weight vector, using least squares. So I'm going to iterate between generating targets, solving or trying to sample this worst case model just once, assuming that my previous model is correct, and then regressing it once again. So this is it's not clear why that would work, but you can show that in fact it does. You can iterate between policy evaluation and improvement. You can do it in deep Q learning, and you can do error bounds, and you can even discover that you're not good, because if your regression here is if you're not converging properly, you can discover that you're not really doing that great. Okay, so that's nice, but there is one feature of this problem which I think is fascinating. So let's recall the American put option that we saw before. So this is a problem where you basically you want to know you can sell the asset at price K up to maturity T. So whenever you're above price K, you want to execute, but you don't want to execute too early. So the question is when to execute, and of course you want to maximize your expected payoff. That's, as I said, a very well-known problem in finance. So we did some simulations. If I knew how to make money, I wouldn't have told you so. And the price transitions, we estimated them for historical data. And the robust value is to consider the estimation uncertainty. So we only have that many transitions in a day. We only have that many days that are relevant. The amount of data is not that large. So what's interesting here is that we did the following experiment. So we assumed in our model that the transition depends on the price. So we built a simulator where we have a mean reverting process. But for the estimated model, we have a constant transition. So there was not a transition where up or down with a given probability depending only on the price, not on the mean reverting price. So there is a real mismatch, not in the parameters, but also in the model class. And what we see here, this is A is a number, and on the y-axis we see the probability that your return is going to be more than A. So you never lose money in American option. You lost money before when you bought it, so you never lose money. So you're always going to make above zero. And what you see here that when you solve the nominal models, when you solve the nominal MDP, your graph is way below the robust MDP, but the robustness here is geared toward a model which is not the true model that generated the data. So this phenomenon of model misspecification is quite interesting. So what you can gain by robustness is that you can solve not the right model, but still get a pretty good policy. So I think that's pretty interesting. What I'm going to do now is I'm going to talk about risk-sensitive policy. I'm going to talk about CVaR, conditional value at risk. CVaR is the measure Emma introduced. I just briefly mentioned it today. So CVaR at quantile alpha, basically you compute the alpha worst. So think about alpha like 5%. This is the conditional expectation given that you're in the 5% worst quantile. Also known as the expected shortfall, sensitive to rare disastrous events. As long as alpha is not very small, it's very easy to estimate. So to estimate the mean, you can do something like that. You can take the empirical mean. To estimate the CVaR at alpha, you take the alpha and worst samples, and you just average them out. So as long as alpha is not tiny, you should be okay. So for CVaR, we know that in general it's hard to compute to optimize the CVaR, and the question is if we can come up with a gradient algorithm. So we have the classical encoding of policy by parameters, but at least in finance, people have looked at a pretty weird situation. So they looked at the case where their parameters do not affect the system, so they only affect the payoff function. So we're looking at the situation where your parameter affect everything. So this is the standard objective, or maybe a risk-sensitive objective. By the way, this is usually what people care about. So maximize the expectation subject to CVaR above the threshold. Think about it like that. You want to maximize your expected return of your portfolio, but you don't want the worst year in 20 years to be really, really bad. So in stochastic programming in finance, people worked on the following problem. You have a portfolio. It's going to affect your payoff function because it affects your allocation, but your portfolio is too small, so it's not going to affect the whole market. So this is something that people have done in the past. In RL, we do need to think about what happens when you affect the system. I want to mention just briefly that there is I talk about financial problems. That's my own personal disposition. But robotics and healthcare and also power grids are all problems where risk is really important. And CVaR has been used in power grids, for example, in planning, in long-term planning. If you live in California, you might not be so happy about the choice of let's plan for the worst thing that will happen in 20 years. So what's the approach? We estimate the gradient and come up with a new gradient formula. It's pretty cool that you can give the proof in one slide, and then you build a sampling-based estimator and do an SGD on the policy. So let's remind the gradient estimation likelihood ratio method due to Glynn. In about 40 years ago. 30 years ago. So how do you estimate the gradient of the expectation? This is think about it, the gradient that will go into the deep network. So the gradient of the expectation is the gradient of the integral. You can put the gradient inside, multiply and divide by f of x, just rewrite as expectation, and then you can approximate the expectation as an empirical mean and use the law of derivatives for that. So this is pretty easy, right? I mean, to estimate the policy gradient, we know how to do very well. So to estimate the gradient of the CVaR, maybe what we should do is do exactly the same thing that we had did before, but just now sum over the alpha n worst sample. So I'm going to enumerate my alpha n my samples, take the alpha n worst, and do the same trick as before. So that's not going to work, and the reason is because of Leibniz integral law, calculus 101. And the reason is that if you're taking a function that depends, and you're taking the gradient of a function where the integral limits depend on the parameters themselves, so here Q is the quantile, but the quantile itself depends on the parameters of the policy, then you need to take that into account. You cannot assume that this is not influencing. So basically just taking one more step with the integral law, and you need to take the derivative of the quantile itself with respect to the parameters. So you need to correct your gradient formula. And the proposition is that the gradient of the CVaR equals the expectation of what we had before, but now you also have to deduct the quantile. And here everything, the quantile and the return, depend on the parameter vector. So the estimation algorithm becomes really simple. It's almost like what you would expect. So the gradient of the CVaR is you sum over the alpha and worst samples, but now you need to correct them with the empirical quantile. Now the issue is that the empirical quantile is not unbiased, not an unbiased estimator, so you still need to go through some math and show that this bias is not very large. and you can show convergence. You can prove that SGD is going to get you what you want. Okay, so we know how to solve, or at least get locally to the optimum of the CVaR. Let's see how we're doing on an RL mock application. So in this mock application, this is a Tetris that we all know and like. You get a bonus for cleaning multiple rows, and we compare a standard policy gradient with the CVaR SGD version. So this is really optimizing the CVaR. So if you look at the histogram of the total reward for the standard policy gradients, you get something like that. So basically, it is well shifted from the blue part, which is the CVaR policy gradient. And indeed, the average reward is significantly higher. So the average reward policy optimizer is really much better in terms of average reward. That's expected. But the quantile, that's really what you care about. So you look at the quantile, or the quantile of the CVaR is lower than the quantile of the expected reward. So at this point, you would say, what is happening here? So this is really what is happening here. This is, we're zooming in on what happens when the number of rows that you clean is very, very small. So only 100 rows, 200, 300 rows. And here we see that the standard policy gradient is just going to be, the frequency of getting the left tail for average cost policy gradient optimizer is just much higher than for the CVaR, and indeed the CVaR itself is much higher comparing to the average reward, what the average reward is going to get you. So what we see here is that when you optimize the CVaR, it's basically to protect yourself against the worst possible events. You're going to limit them at the expense of having a worse average performance. And the question is, what do you prefer is really your problem. It's really up to you to decide. Okay, so intuitively, when you look at that, you say, well, it seems that there is something here that is akin to robustness, meaning that I'm not going to get really, really, really bad results. And that's going to make my policy more robust, at least in that sense. So what you can show is the following. Remember that we said before that risk awareness is similar to robustness. So what I'm going to show you now is a sample result where we show that risk awareness is exactly the same as robustness. And the claim is this is a very general result, which I'm not going to get into to avoid a mathematical clutter. But whenever you have a risk-aware optimizer, essentially you're solving a robust optimization problem. And it's really only the question of which robust optimization problem. So let's look at that at CVaR and model uncertainty. So consider the following uncertainty model. So in this model, then you will look at multiplicative perturbation. So I have a nominal model, the conditional probability of ST plus 1 given ST and AT, and it's multiplied by some number. This is going to be the uncertainty value. And so the set of all possible perturbation is p hat. And now I'm giving an uncertainty budget. So basically there is a budget here. That's a multiplication. So delta 1, delta 2, and so forth. I count over all my states. And I limit the level of deviation by eta. So basically I have some budget eta. If eta equals 1, then there is no uncertainty. If eta is more than 1, then there is some uncertainty. And the motivation here is that not everything can happen. Not every bad thing can happen at the same time. This is a fairly weird set. The set is non-convex. It's not a nice set to work with. Right? Everything is correlated. It's not. You cannot write it as a multiplication of sets. It's an ugly beast. This thing. But still, it's an uncertainty set. It has an intuitive meaning of having some level of uncertainty budget. And I think you can show many things about it. But the most important things from our perspective is this result here, that the conditional value of risk equals robustness. And the equality here is algebraic. So basically, whenever you're solving CVaR of the best policy for the sum of rewards, it is exactly the same like finding the worst possible model from this weird uncertainty set. So what you get here is that you can rewrite conditional value at risk as a robust optimization problem. And in fact, this holds for a very large family of risk measures. So every consistent coherent risk measure, and I'm not going to get into that, had an equivalent robust optimization problem. So the two are really the same. Okay? And it's a small miracle that for CVaR, we can write such a simple set. So this is a really simple set, right? Like I can write it in one page. It has some intuitive meaning. Perturbations are correlated across time, but still, it is a very fairly simple optimization problem. So I think that's quite interesting. And before I move to the next part, are there any questions? All right. So now I'm going to talk about the two pending issues in robust optimization. Those are two recent papers. The first one is, how do I find my uncertainty set? So I know how to solve a lot of robust optimization problems, but then my uncertainty set should come from somewhere. The question is, how do I find it? How do I construct it? How do I adjust to it? And the second question is that of online adaptivity. So in the formulation so far, we always say that we build the uncertainty set in advance. But maybe I can see some data, shrink my uncertainty set, or enlarge it to accommodate for what I actually see. So we'll start with talking about uncertainty set construction. So we came up with a very simple model. We call it the trembling hand model. So you want to play policy pi, and you play it with very high probability. Now then with a small probability alpha, your hand sort of trembles and you move to another policy, which is potentially adversarial. So, and we call that action robust. So basically you want to find a policy pi that is going to behave well, even though that you're not going to really play pi, but rather you're going to play this mix. And if you want to think about it from a continuous control perspective, so you choose an action A, but the adversary can modify it to, instead of A, to something which is not so far from A, but rather 1 minus alpha A plus alpha A prime, where A prime is chosen by an adversary. So that's why we call it action robust model. You need to pick the A while thinking that somebody's going to modify it for you. So what's the intuition here? So the intuition here that as you're doing something like that, you cannot choose corner cases. Like you need to be able to know that if you're going to choose the corner case, the adversary is going to push you over the limit. So the adversary is just going to push you a little bit too much so that you're not going to choose something which is too risky. And if that's the case, then that's going to build in the robustness. So this leads to an algorithm that looks a little bit like GANs. So we call it ARDDPG. So basically you find the optimal actor policy. You learn the best adversary against a one-step greedy policy. You evaluate the joint policy, so you evaluate the pi mix, and you do that all the way. So you have an actor, a critic, and now you have an adversary. And this really looks a lot like a generative adversarial network, and it really is. So this is just to show you how the results look like. This is with a hopper problem. So this is a hopper, and we modify there is a noise here, so there is control noise, and there is a relative mass. I'm sorry, this doesn't look so well on the large screen, but basically yellow is good, yellow is good, red is bad. This is the probability of the noise. So 0 is no noise, 0.5 basically you can't do anything, and then this is the relative mass. So when you look at the action robustness solution, you solve for at least for a small noise. This is a continuous model and this is a discrete model. They don't really vary that much. You do something which is a lot better than the classical approach, and you see that even when you compare to the baseline, you get a much better result in terms of reward as a function of the relative mass. So this is basically you're doing a lot better when you can when you're solving a robust problem. You're even doing better than when you solve a robust problem without any noise, which can be a little bit surprising, but this is in a very small data regime. So you have very little training here. So you get robustness, you get transferability, you can, and you do not need to define the uncertainty set explicitly, because essentially you learn it through data, because as you simulate the worst possible case. Okay, so this was problem number 1. Now I'm going to talk about problem number 2. The problem number 2 is that as I have a single trajectory, I get data. When I get the data, I might be able to change what my estimation of the uncertainty. And the question is, how do you do it? So one way to do it is try to construct things online. And with that, we adopted a pseudo-Bayesian approach. So the idea is the following. You have a model. In the model, you have a Dirichlet distribution over the next states. So you think that the next state is going, you have a distribution over distributions. You observe the history up to time h. And then you build an uncertainty set. So this uncertainty set, you have some nominal transitions. That's a p hat of S and A. And you look at all the transition distributions that are at norm 1 bounded by something. This is a design parameter from your nominal distribution. So now we have an uncertainty set. This uncertainty set is a rectangular set, meaning it's a product set of all the uncertainty sets per state action. And you can update it online. Now this is pretty simple to update, right? You don't need to think much about it. You just need to estimate the nominal. That's, if it's the Dirichlet prior, it's trivial. And you need to figure out what are going to be the design parameters. And that's something which is arbitrary. So you have an uncertainty set. You can easily compute it from data. Now comes the tricky part. So instead of thinking of Q values as functions, you think about them as random variables. And you solve what's known as the robust Bellman recursion or robust Bellman equation. And that's the equation that is written here. So let me explain. The distribution of the Q function equals the distribution of the reward. We can have a prior over the reward as well, prior posterior, plus a discount factor times the worst possible model in our uncertainty set of the next state and the Q function. So this is a recursive Q function, and you can compute this Q function as you go along. So this is something that is known. This has been done by others. It may look difficult, but it's not particularly difficult to compute. It's something that you can do in distribution, and it works quite well. Okay, so now everything is becoming. Now comes the tricky part. So when you want to solve a Bellman equation or recursive equation, usually we are trying to solve for the expected reward. But there are results, some of them quite old, due to Sobel in the 80s, where you can try to solve for the variance. And this is the variance of the Q function. This is really what's written here. So the variance of the Q function equals the variance of the reward plus the gamma square, because we're talking about the variance, it has to be square. And this is a recursive equation. Why that equation is true? Well, it's a little bit difficult to explain, but it turns out there is a contraction operators that works on the variance as well. So this is a question that has a unique solution. And now, if you believe this whole Bayesian mambo jumbo, then you have the Q function and you have the variance. So you can now approximate the Q as for example, the normal distribution with mean Q, so this is the Q here, and variance W. And W here, let's say you can make it diagonal. So what the key aspect here is that the uncertainty robust Bellman equation for the variance has a unique solution. And because it has a unique solution, you can now think about the Q function as really a Q random variable for which you can estimate the mean. That's what's written here. You can estimate the mean easily by taking expectation over this equation. But also you can compute the variance. Okay, so now everything becomes kind of interesting. So you can approximate everything by deep learning. So you have here the observations, you have your hidden layers, you have the robust layer. This is going to give you Q. At this point, you would normally stop. You would say, I'm done. I have the Q function. Whether I'm doing exploration or not, this is the Q function that I can use for a given policy pi. And at this point, I'm done. But you also have the variance layers. And the variance layers are building this variance estimate. And those variance estimates you can now use to compute your control. So how would you go about it? You're going to say, well, I have my Q value is really a random variable. The mean is what I get from the usual robust operation. The variance is what I'm getting from the layer of the uncertainty robust Bellman equation, and that's it. So I'm going to sample from it, choose a maximizer, and move on. Let me show you an experiment here. This is with cart pole. So what we see here, this is the pole length is changing, and we're looking at the reward. So the blue here, that's robust DQN. That's what happens if you ignore the part here and just look at the robust Q value. So you see that you get something which is very even. It's basically going to be extremely pessimistic. If you're just going to use DQN, you're going to do well when the pole length is small, but then your performance are going to crash. And if you're going to do the DQN with some other improvements, then you're going to be extremely sensitive. And when you're using the robust DQN, then you get things which are the performance is more or less maximized across pole length. But there is something else which is happening here, which is interesting. This is a more interesting graph. So here we change the pole length during runtime. So we change it at this point and at this point, and we see what happens to robust DQN. Basically, it keeps going. It doesn't crash, it doesn't go to zero, but it's not improving. And we see what's happening to our approach. So basically, things change here, but the change so the problem is actually a little bit easier. So performance improve, and the change here again, and the problem is not much more difficult or much more easier, so the performance more or less keep the same. So what we see here is that you can adapt online to changes with this approach because of its Bayesian, or to be more precise, pseudo-Bayesian nature. So there are a lot of things that we can say about those approaches. I think the main interesting aspect here is the connection to Thompson sampling. The sampling stage or the policy selection stage is really a Thompson sampling kind of update, and you can prove a lot of interesting things about them. For example, they're doing safe exploration because they will not let you do something which is too risky. Because of the Bayesian approach, they'll always give some probability to really bad things. Okay. So I have two conclusions to offer. The first one is about risk sensitivity. So risk sensitivity is great. You should do it. CVaR is robustness. It works at scale. If in doubt, then you should do it. It also gives you a good explainability because often you can simulate the worst possible cases and you can justify what you're doing, not in the way of being able to textually say it, but just saying with there is some negligible probability that something really bad is going to happen, and therefore I'm taking a particular actions. There are really interesting applications in energy and finance, which I do not have time to discuss, but it's really something that you should consider when you're trying to solve a real problem. And the conclusion for the whole talk is about what are the problems that we should look at. So I think that RL is data and representation in algorithms. That we all know, but it's also about building algorithms that are aware, that are accountable, that are adaptive, that can be debugged somehow, and that are scalable. And one thing about full autonomy, so full autonomy is very, very far away. I don't think we're that close to full and complete autonomy. And I would also argue that RL works best when you have a stochastic problem, you have a good simulator, and definitely when you have high throughput control. Unfortunately or fortunately, depending if you're worried about your job or not, the real world is usually neither high throughput, and usually you don't have a good simulator. And the key is to work on applications and the lesson to learn for them. And for me, application is something that you get real money to